A PN junction is the building block of many semiconductor devices like diodes, transistor, IC chip, etc. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. Here now we are considering PN junction formation. Consider a thin P-type silicon semiconductor wafer. By adding precisely a small quantity of pentavalent impurity, a part of the PSI wafer can be converted into an SI. There are several processes by which a semiconductor can be formed. The wafer now contains P region and N region and a metallurgical junction between P and N region. Two important processes occur during the formation of a PN junction: diffusion, drift. We know that in an N-type semiconductor, the concentration of number of electrons per unit volume is more compared to the concentration of holes. Similarly, in a P-type semiconductor, the concentration of holes is more than the concentration of electrons. During the formation of PN junction, and due to the concentration gradient across P and N sides, holes diffuse from P side to N side and electrons diffuse from N side to P side. This motion of charge carriers give rise to diffusion current across the junction. When an electron form diffuses from N to P, it leaves behind an ionized donor on N side. The ionized donor has a positive charge, is immobile as it is bonded to the surrounding atoms. As the electrons continue to diffuse from N to P, a layer of positive charge on N side of the junction is developed. Similarly, when a hole diffuses from P to N due to the concentration gradient, it leaves behind an ionized acceptor, a negative charge, which is immobile. As the holes continue to diffuse, a layer of negative charge on the P side of the junction is developed. The space charge region on either side of the junction together is known as depletion layer, as the electrons and holes taking part in the initial movement across the junction depleted the region of its free charges. The thickness of depletion layer is of the order 1/10 of a micrometer. Due to the positive space charge region on N side of the junction and a negative space charge region on P side of the junction, an electric field directed from positive charge towards the negative charge develops. Due to this field, an electron on P side of the junction moves to N side and a hole on N side of the junction moves to P side. The motion of charge carriers due to the electric field is called drift. Thus, a drift current which is opposite in direction to the diffuses current starts. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on either side of the junction extend, thus increasing the electric field strength and hence drift current. This process continues until the diffusion current equals the drift current. Thus, a PN junction is formed. In a PN junction under equilibrium, there is no net current. The loss of electrons from the N region and the gain of electron by the P region causes a difference of potential across the junction of the two regions. The polarity of this potential is such as to oppose further flow of carriers so that a condition of equilibrium exists. Figure shows a PN junction at equilibrium and the potential across the junction. The N material has lost electrons and P material has acquired electrons. The N material is thus positive relative to the P material. Since the potential tends to prevent the movement of electron from the N region into the P region, it is often called a barrier potential. This is the case of a PN junction.